I'm Michael Derenbecker, and this is my senior design project. My project is called the DC Treasure Box. My primary target demographic are undergraduate EE and CPE students. The product is designed to be an affordable option to those who want to have a mobile workstation that they can use to test circuits and components. An all-in-one DC resource box would enable electronics students to prototype circuits for labs and projects without the need for lab equipment present on campus. The labs on campus can be physically far, closed, or overcrowded, preventing students from accessing the equipment. There's a significant need for a product capable of providing standard lab equipment functionality. The functionality this project provides are positive and negative DC power supplies, 4-quadrant SMU, analog inputs and outputs, digital inputs and outputs, and other multimeter-like functionality. This functionality is capable of acting autonomously, allowing for fast measurement sweeps. These measurement sweeps can be used for the characterization of circuits or components. Characterization and validation of circuits can save lab time and aid in debugging. In this video, I will give a brief overview of each subsystem, its capabilities, and what it can be used for. Afterward, I made a demo showing the project in action by completing several experiments. The first board I'm showcasing is the power supply board. This board has 3 output channels. 2 of those channels are adjustable 0 to 12 volts, and 1 of those channels is adjustable 0 to negative 12 volts. Each channel has a overcurrent protection where a shunt resistor measures the current delivered to the load and trips a comparator if an adjustable threshold is exceeded. The typical overcurrent protection turn-on time is 50.9 microseconds. This was achieved at a microcontroller clock speed of 3 MHz. If the clock speed is increased, the transient response time will decrease. The power supply output current is spec'd at 100 milliamps, but is more than capable of supplying at least 200 milliamps to a load, especially at higher voltages. The limiting factor in the maximum output current is the power dissipation of the series pass element transistors. These transistors are in the TO220 package, which are capable of dissipating at least 1.5 watts of power and can have heat sinks mounted to them in order to increase that dissipation. This amount of current is more than enough to power most undergraduate projects. The power supply output voltage accuracy is specified at plus or minus 1% plus 5 millivolts. The next board I'm showing is the multimeter board. This board has a grand total of 16 inputs or outputs. Of those 16 outputs, 8 of them are digital and 8 of them are analog. Because there are 4 analog inputs, 4 different nodes of a circuit can be probed at once. This can be enormously useful for larger circuits or circuits where multiple voltages of interest occur. Of the 4 analog outputs, 2 of them are plus or minus 5 volt capable and 2 of them are plus minus 10 volt capable. The analog outputs have an accuracy specification of plus or minus 0.1 plus 1 millivolt. These outputs are also capable of delivering more than 20 milliamps of current to a load. This ensures that other loads don't drag the voltage down. The analog outputs are designed to be used as voltage references. These could be useful when sweeping different values having a precise input voltage to, say, an op-amp or a transistor. They're also capable of providing DC biasing for circuits. The digital outputs are actually analog outputs, just with a pretty bad resolution, only 8 bits from 0 to 5 volts. But the circuit is designed to drive large capacitive loads with fast rise times. The reason the digital outputs actually output analog voltages is so that multiple logic families can be supported. The 4 digital inputs each have their own individual threshold setting. This threshold setting would be the average of the output logic levels of the digital circuit being measured. For example, from a TTL gate, VIH is around 2 volts and VIL is around 0.8 volts. Therefore, in order to properly distinguish between the 2 output levels, the comparator will trip at a voltage of 1.4 volts. The SMU board is capable of forcing positive and negative currents while measuring voltage, and outputting positive and negative voltages while measuring current. When in voltage mode, the SMU is capable of outputting a maximum of plus or minus 10 volts. This is done with an accuracy of plus or minus 0.5 plus 5 millivolts percent error. When in current mode, the SMU is capable of outputting a range from plus or minus 100 milliamps. This is done with a percent error of plus or minus 0.5 plus 25 microamps. This board also has current and voltage limiting. Unlike the power supply board that simply turns off the channel if a current threshold is achieved, the SMU will either go into a constant current or constant voltage source mode when a overcurrent or voltage event occurs. When an overvoltage event occurs, diodes limit the maximum load voltage to around 0.7 volts above or below the threshold. The shift into constant voltage mode takes around 100 microseconds. When an overcurrent event happens, the shift into constant current mode takes around 500 to 700 microseconds. The SMU is very useful for characterizing nonlinear components, such as diodes or transistors. The last board shown is the microcontroller motherboard. The microcontroller slots in to the motherboard. This board is also responsible for distributing signals and power to each of the subsystems. This board also has 3 relays, which allow for construction of an ohm meter with 4 different ranges. Unfortunately, the ohm meter did not immediately work, and not enough time was present in the quarter to properly debug it, and thus is untested as of now. The last thing to talk about is the power board. This board was not designed by me, rather purchased. This is a standard buck boost converter that takes a positive input and outputs plus minus 15 volt outputs. I also prepared a little demonstration video showing each of the subsystems working together autonomously to complete different experiments. Some of these experiments were directly pulled from lab manuals, and some of them were concocted by me. Thank you for watching.